Given the equation y times the natural logarithm of x to the fourth plus y cubed plus 4 equals 2, evaluate dy dx. Assume that the equation implicitly defines y as a differentiable function of x. So, to begin here, let's recall the theorem for implicit differentiation in Rn. Voila! So, we are going to let a function f of x y equals 0 be differentiable on its domain. And now, if we suppose that the function f defines y as a differentiable function of x, then we're able to conclude that dy dx is equal to minus the partial derivative of the function with respect to x by the partial derivative with respect to y. And this is, of course, such that the partial derivative with respect to y cannot be equal to 0. So this is the theorem that we're going to use now to evaluate dy dx. So let's simply start here by rewriting the given function. So we are given the function y is equal to the natural logarithm of x to the fourth plus y cubed plus 4 equals 2. But we want to go ahead and now set this equal to 0 for simplicity. So we can rewrite this function as y multiplied by the natural logarithm of x to the fourth plus y cubed plus 4. And now if we subtract 2 from both sides, we're left with minus 2 equals 0. Beautiful! So now that we have rewritten this function, we're all set and ready to find all the partial derivatives. So we want to find the first order partials. So we first want the partial derivative of this function with respect to x. So we can see here that we only have one x within the argument of the logarithm. So differentiating, we have y, and this is all multiplied by the derivative of the argument of that logarithm, which is 4x cubed, all divided by the original argument, which is x to the fourth plus y cubed plus 4. And that 2 differentiates to 0. Beautiful. We can leave it like this. There's nothing wrong with this. Or we can rewrite this as 4 times x cubed times y. And that is all divided by x to the fourth plus y cubed plus 4. Beautiful. Now, we also need the partial derivative of this function with respect to y. So this is the slightly more exciting case because we have two y's. If we look back up at our original function, we have this y on the outside as well as a y within the argument of the logarithm. So we need a product rule. So by the product rule, this will differentiate to 1 times the natural logarithm of x to the fourth plus y cubed plus 4 plus y multiplied by the derivative of the natural logarithm with respect to y. So that's going to leave us with 3y squared, all divided by x to the fourth plus y cubed plus 4. And again, that 2 just differentiates to 0. So we can rewrite this to make it look a little bit nicer and say that this is equal to the natural logarithm of x to the fourth plus y cubed plus 4 plus 3y cubed all over x to the fourth plus y cubed plus 4. Now, before we dive into finding the derivative dy dx, thinking back to this definition from our theorem, we can see that we're going to have the partial derivative with respect to y in the denominator. So we might as well take an extra minute now and find a common denominator for this partial derivative. So thinking about the logarithm as being over 1, we can now multiply the numerator and denominator of this term by x to the fourth plus y cubed plus 4. Of course, whatever we do to the top, we've got to do to the bottom. So we're multiplying by x to the fourth times y plus y cubed plus 4. Beautiful. So this is now going to leave us with the simplified partial derivative. And so this is equal to x to the fourth plus y cubed plus 4 multiplied by the natural logarithm of x to the fourth plus y cubed plus 4 plus 3y cubed. And that's all over that common denominator, x to the fourth plus y cubed plus 4. Whew! Alrighty, so we have everything that we need now, and we're ready to find dy dx. Again, we know by definition by the theorem for implicit differentiation in Rn, that dy dx is equal to minus the partial derivative with respect to x by the partial derivative with respect to y. So, in the numerator, we have 4x cubed y, and that is all divided by x to the fourth plus y cubed plus 4. Now, this is all divided by that partial derivative we just found. So the big old derivative, we have x to the fourth plus y cubed plus 4 multiplied by the natural logarithm of x to the fourth plus y cubed plus 4 plus 3y cubed. And this whole expression is divided by x cubed plus, or excuse me, not x cubed, that should be x to the fourth plus y cubed plus 4. Whew. So look at this monstrosity here. Can we simplify? We sure can. We can recall that fractions in the denominator flip, or we multiply by their reciprocal. So we can rewrite this as minus 4x cubed y, and that's all divided by x to the fourth plus y cubed plus 4. And now multiplying by the reciprocal of the denominator, this is now x to the fourth plus y cubed plus 4. And that is all divided by x to the fourth plus y cubed plus 4 multiplied by the natural logarithm of x to the fourth plus y cubed plus 4 plus 3y cubed. And look at this beautiful simplification we have. We have the like terms in the denominator will cancel each other out to 1, leaving us with a beautiful final answer for dy dx. And dy dx here is equal to minus 4x cubed y. And that is all divided by x to the fourth plus y cubed plus 4 multiplied by the natural logarithm of x to the fourth plus y cubed plus 4 plus 3y cubed. And so there you have it. This is our beautiful final answer for the derivative dy dx in R3.